Can we start? We are.
I think we can start. Mani is trying to connect to the computer, so just a few seconds. I mean, you can start introducing him if you want.
Okay, so welcome back to everyone, and welcome to those joining for the first time the meeting for this session. And thank you for being here. I am Mara De Ioannou from CNR Italy, and I'm going to chair this session. And this session will have the same format as the previous one. So we will have 2 talks and then a long Q&A discussion session. And please write your question in the chat, but we invite you to join in person the discussion. Let's ask that, and we will pull in Zoom panel session. This session will focus on transversal topic that is kinetics. That is a key point for whole application we could think on ammonia combustion, and on ammonia oxidation in mild combustion condition. They pose further issues on kinetics and some insight on the process itself. So let's start with the first speaker, but someone says that cannot hear me. Gaetano, you can hear me? Okay, okay, thank you.
Yeah, we can hear you, but...
Okay, thank you. So, okay. So the first speaker is Mani Sarathy. Mani is an associate professor of chemical engineering and the associate director of a Clean Combustion Research Center at KAUST. And his major research interests are sustainable energy technologies for reducing environmental impact of energy conversion systems. And we will know that he is a worldwide recognized leading expert in development of chemical kinetics models for conventional and alternative fuels combustion, and also for pollutant formation, with the support of advanced numerical and theoretical tools and experimental approach in model reactor and advanced diagnostics. So, Mani, the floor is yours.
Thank you, Mara. Is the screen showing on the Zoom?
Yes, yes.
Okay, very good. Thank you. So I'm presenting here in person. Thank you, Mara, for the introduction. Thank you all for attending. So I'd like to acknowledge first my team members, Dr. Xiaoyan Zhang and Dr. Manuel Palacios, for contributing to this. So today, I'm going to be talking about ammonia combustion chemistry. And as we've heard already today, earlier, a lot of interest on the effect of hydrogen blending. So also I'll be focusing on how does hydrogen actually impact ammonia combustion chemistry, as well as other species involved in the typical ammonia reaction mechanism. So as we said, it's a nice carbon-free molecule and a promising hydrogen carrier. We can make ammonia from fossil fuels. With carbon capture, you get your blue ammonia. From renewable energy, such as solar and wind, you can get your green ammonia. And on the upper side, we can use, you see how we can use ammonia as a carrier for hydrogen and burn that ammonia directly in engines for propulsion, stationary power generation, or even use it in fuel cells for electricity generation. And in addition, we can use it as a fuel directly rather than generating like hydrogen as an intermediate. So if we want to use ammonia directly as a fuel, well, we know that the laminar flame speed is low, the flammability range is low, so because of the limited reactivity. But hydrogen, on the other hand, has a high reactivity. Not loud enough? Okay. It's not loud enough?
No, it's good for us, but not for the...
Oh, for the... They cannot hear?
No, maybe you want to switch.
So they could not hear online? Okay. Okay, I hope it's better now. Yeah, so hydrogen has a high reactivity, so it's a good potential for blending ammonia with hydrogen. You can still produce your zero carbon emissions. You can still enhance the intensity of ammonia combustion. And this type of option allows for mitigating some of the safety concerns with burning hydrogen directly. But this was a nice PhD thesis I saw recently from Cardiff University, 2019, by Al-Bashmina, as it was a PhD candidate. And what they show here is an ammonia burner, okay? And after the burner, they add a bluff body. And within this bluff body, there are some coils, or essentially a heat exchanger. They pass the fuel into that bluff body, which is heated by the post-combustion gas. And the fuel is cracked and fed back to the inlet of this swirl burner. So essentially, you get a mixture of hydrogen and ammonia. And depending on how they operate or design the coils inside, and also depending on the amount of airflow, they can actually vary the temperature inside of this bluff body and get different amounts of cracking. So I thought that was a pretty interesting concept for precracking of ammonia. Another interesting thing they showed, which was only by simulations with, I'd say, rather preliminary kinetic models, is that by injecting part of this post-cracked fuel stream after the burner and before the cracker, they could actually reduce the NOx emissions. And so there's a role of the ammonia and the hydrogen in the post-combustion gas to control NOx chemistry. And I think these types of concepts are good. And in this presentation, we might see some of the chemical reactions which are responsible for governing those different types of phenomena. So one is, of course, the stability of the ammonia combustion with hydrogen blending, but also the effect that it has the cracked hydrogen ammonia mixture on post-combustion NOx control. As in any combustion chemistry study, we take a three-tiered approach. We start with looking at the theoretical calculations, mapping out what's in the literature in terms of potential energy surface calculations, kinetic rate calculations, and trying to adopt the latest in terms of theory, as well as basic experimental measurements into our more comprehensive chemical kinetic models for ammonia hydrogen mixtures. Then we also looked to the literature and facilities that we have available at KAUST for validations of both kinetic rates, but also kinetic models against ignition delay times, flame speeds, stirred reactor speciation, and so on. And finally, attempt to develop a comprehensive model, one that covers different aspects of combustion, all the way from pyrolysis to oxidation, and for different types of flames, homogeneous conditions, speciation for ammonia and for its mixtures with other gases, which we'll see today, including NO and hydrogen. So if you want to develop comprehensive kinetic models, we typically have an approach where we start with base models describing the core chemistry. I think there's been a lot of work in the combustion community on hydrogen oxidation. Some recent ones that are very good include the Burke and Klippenstein recent kinetic calculations for many different H+O2 type reactions, and Glaborg in 2015, a very comprehensive kinetic model for hydrogen. These include state-of-the-art use of thermodynamic active thermochemical tables for having accurate thermodynamic data on the model. And then on top of that, you need to build your ammonia combustion model. And in the presentation, I'll try to show there's been lots of work in kinetics community for many of the reactions in the ammonia combustion network. These include rate coefficient data for ammonia, but other and nitrogen related species in the reaction network, the effect of NO as well. And then also we need experimental data, of course, to validate these models. So the community has done a lot of work in terms of generating experimental validation. The interesting things we can see in roughly the ammonia mechanism, we'll go into detail later, but ammonia breaks down to NH2, and then NH and N, that's the main linear path, but as in the presence of oxygen, you have NOx formation mechanisms, but you also have Denox reaction mechanisms, and both need to be considered in ammonia combustion chemistry. And the data, if you want a comprehensive kinetic model, we need to go to the literature and to the different groups around the world and find what kind of data is actually available. So we typically start with pyrolysis. So ammonia and N2H4 hydrazine are hydrazine being an important intermediate in ammonia combustion. Then, of course, the effect of NO as well as hydrogen on the combustion of ammonia, the Denox mechanism, so ammonia plus NO and NO2, ammonia oxidation as a pure component, and then ammonia hydrogen oxidation. And as we'll see in the presentation, community has done a lot of work in generating data for all these different systems. I won't be able to show all of these subclasses in this presentation. I'll focus on the main ones: pyrolysis, Denox, and then the oxidation experimentals data that's available and models that have been used to validate against those experiments. So first, we can look at pyrolysis of ammonia and hydrazine. If we look on the right-hand side, in the absence of oxygen, ammonia dehydrogenates to form NH2, NH2, then dehydrogenates to form NH, and then down to N, eventually a molecular combination to make nitrogen. And the side pathways then include recombination of NH2 to make hydrazine, N2H4, which also dehydrogenates to make diazine, N2H2. So the critical reactions typically in a pyrolysis mechanism are initially the ammonia hydrogen removal, and then the hydrazine formation and the diazine formation. And there was nice work already more than a decade ago by Klippenstein, high-level quantum chemistry calculations, and then experimental measurements at Stanford for hydrazine formation. And we can see there's pretty good kinetics already available in the literature for these important pathways. And then the groups at Stanford and others have also developed in shock tubes pyrolysis data for ammonia across rather broad ranges of temperatures from 1100 all the way up to 2800 Kelvin, and then moderate pressures. And we can see here that plots here are shown for the species times history. On the left-hand side, it's for NH2. And we can see here as in the shock tube, species time histories are fairly well calculated by different kinetic models. Here we have kinetic models by Shrestha in 2020, 2021 at the last symposium, Glaborgs from the recent PEX article in 2018, the group at Polemy by Stagni et al. Had a model also in 2020, Galway, the group in Japan at Tohoku Nakamura about 5 years ago, and our own recent model at KAUST. So in terms of pyrolysis, when we look at ammonia pyrolysis and species time histories for NH2 and products, in shock tubes as well as for hydrazine pyrolysis or ignition, we find pretty good agreement between all the different models. Really, there's not much in terms of chemistry that's missing in the pyrolysis. And in the terms of speciation also, we can find Shrestha's recent model and Galway's as well as our own are able to predict these species profiles fairly well. Once we start looking in the presence of oxygen, ammonia will form NO. So then you need to be concerned with the Denox mechanism. Good thing is that Denox is not a new topic in the combustion community. There was already studies in the 1990s looking at the effect of ammonia and NO for the reason that ammonia is used in Denox applications such as SCR in typical combustion systems. So many researchers have actually done experiments of ammonia plus NO for the purpose of looking at how NO could be reduced. And this types of chemistry, of course, we can readily adopt into the ammonia combustion model. So the major reactions of importance are the interaction between NO and NH2. NH2, the first radical formed after you remove hydrogen from ammonia. And you have a very important chain branching reaction to form NNH plus OH. So here you're taking NH2 and you're forming a very reactive OH radical. And this, of course, makes the system much more reactive. But at the same time, we have a competing chain termination reaction where NH2 reacts with NO to form N2 and water. And this is upper chart on the right shows a summary of different rate calculations and experiments done for the overall rate. So this is NH2 plus NO for all products. And this is from Glaborg's PEX paper in 2018. So experimental measurements have measured the overall rate. There's a range of theoretical studies, which from Song, from Klippenstein, which are able to accurately capture the total rate. However, where there's a big difference, and even in the paper of 2018 by Glaborg, it was noted, was in the branching ratio between these two reactions. So the first reaction, the chain branching, I'm sorry, there's a typo, this should be the K of the chain branching reaction divided by the total rate. I think we have a font issue here. So it's the branching ratio is the K of the branching reaction over the total for both reactions. And we have some experimental measurements, but there's a large scatter. And you can see here different calculations from Miller and Klippenstein in the dashed, and then Klippenstein's more recent calculation in 2017, the dashed green line, and even different levels of theory, be it CAST-PT2 or MRCI have different fittings against experimental data. So the branching ratio, that is the rate of the chain branching reaction divided by the total reaction rate, has some uncertainty. And then we'll see later on that this has implications then on the ammonia combustion, especially the flame speed, flame structure, and the ignition delay time. In Glaborg's 2018 paper, they had to tune this rate to get a better prediction against experimental data. I'll show later on that additional theoretical studies are needed on this work, on this reaction, to get a really accurate rate. Then to validate the Denox mechanism, though, there's a lot of experimental data. So we have flame speed measurements of ammonia plus NO, JSR measurements of ammonia and NO, as well as flow reactor speciation and premix flame speciation. And again, all of this data collected over 30 years in the combustion community in these different papers, and mainly for the reason of looking at Denox chemistry. So the paper by Glaborg in 2018 at PEX came up with an ammonia model which used some tuning for the Denox chemistry, and they're able to fairly well capture NO profiles as a function of temperature in stirred reactors as well as in flames. And some of the other models, such as the one by Shrestha more recently, showed a much lower reactivity compared to the experimental data. And that's again because of uncertainties in the selection of those important chain branching and chain terminating reactions. Then we can go further to look at the high temperature oxidation chemistry. Here, we'll exclude looking at some of the important HO2 chemistry until later. First, let's look at just the important radicals at high temperature. It's going to be H radical and OH. So there's lots of experimental data for ammonia combustion at high temperatures, flame speed measurements, ignition delay times, flow reactor measurements of premixed flames. Most of this data you can say is in the last 5 or 7 years. And of course, pure ammonia as a fuel is only recently of interest to the combustion community. The team led by Lee et al., who was at KAUST, looked also at some quantum chemistry calculations for different high temperature reactions. So this is the NH2 plus H going to form NH plus H2. So again, the hydrogen abstraction reaction. So new theoretical calculations have been calculated just recently in the last 2 years, and also NH2 plus OH to form NH and water. So here we see a big difference between some of previous theoretical studies all the way back to 1991, where rates at high temperatures were about a factor of 2 different than what we get with the latest techniques. But at low temperature, you have huge differences in rates. So we believe in the current study, this was done in 2020, with more of the state-of-the-art quantum chemistry tools available today compared to what was available to the community 20 years ago. We have a better grasp on some of these abstraction reactions by H and OH from NH2. And then if we go to the kinetic models for the high temperature chemistry, looking at flame speeds, laminar burning velocity at different equivalence ratios. Experimental data is available from a number of groups in North America, Asia, and Europe. And the different models are doing already fairly well. And because the uncertainties in the high temperature chemistry, these abstraction reactions are not that large. So the KAUST model, Shrestha in Germany, and Polyme are able to capture the flame speeds and also the effect of pressure on flame speed. And if we look at high temperature ignition delay, also we're able to see that most models developed in the last 3 years are able to capture high temperature ignition delay time fairly accurately. We'll see a lot more uncertainties now when we look at low and intermediate temperature chemistry of ammonia, where models are very different from each other. And it's largely because of uncertainties in some critical reactions happening at anywhere from 800 to 1200 degrees Kelvin. One very important reaction at low temperatures, NH2, again, the first intermediate after abstracting hydrogen from NH3 plus HO2, hydroperoxy radical. This reaction is very complicated because you can get multiple products. First, you could have NH2 plus HO2 going to ammonia plus oxygen. This is a terminating reaction, but it can also happen by an excited state potential energy surface. So we have one channel that goes to form a triplet oxygen as a product and another one that forms a singlet oxygen as a product. And the rates of these two are different. And in previous kinetic models, or in previous kinetic studies, they did not accurately capture the excited state chemistry in the initial potential energy surface calculations. So here on the right-hand side is work that was led by Dr. Monje Palacios here at KAUST. And they calculated the different reactions, the triplet state, the singlet state reaction for NH2 plus HO2 to different forms of oxygen. And you can see here that in the green line, we have, in the green line is a triplet. In the purple line here at the top is the total rate, but R4, which is the triplet, the orange line, is much faster than the one forming the singlet channel. So the triplet channel dominates in terms of this termination reaction compared to the singlet. And it's very difficult, very challenging to deal with this excited state potential energy surface and calculate the rate. There's been recent work by Stagny, also by Klippenstein on the same channel, and as well as the one from KAUST, and there's about a factor of 2 uncertainty still in those differences in theoretical calculations. There's also the R5, the triplet, which is a branching to form OH, so NH2 plus HO2 to form H2NO plus OH. This can also happen on an excited state potential energy surface, transition state, but it's very slow, as we see here in the green line. And the ground state channel, which has been previously studied by Dean and Bozelli, is much faster. So uncertainties, I think, in this triplet channel are still contributing to differences in models, and we can see this here. So this is ammonia oxidation, low and intermediate temperature chemistry for ignition delay times on the upper panels, and then jet stirred reactor oxidation. And we can see, differences of factor of 10 on some ignition delay times around just about around 1000 Kelvin or 1200 Kelvin. And this is largely due to uncertainties in those rates of NH2 plus HO2. In the more recent models by the ones that we have at KAUST and also Glaborg, who use some tunings of these rates, they get better comparison to experimental data for ignition times. But as we go to lower temperatures in a jet stirred reactor, this is from 600 Kelvin all the way up to 1200 Kelvin. We can see that many models published before 2021, 2020 predicted lower reactivity compared to at these lower temperatures because they did not have access to these latest rates for NH2 plus HO2. And then finally, we can look at the oxidation, co-oxidation of ammonia plus hydrogen. Here again, from a fundamental kinetics perspective, there's not much. It's more about what experimental data is available. There's been work done on flame speeds across a range of initial temperatures, pressures up to 5 and 10 bar, ignition delays up to 60 bar, and then also speciation studies done in jet stirred reactors. And you see most of these experiments were acquired in the last 3 to 5 years in the combustion community. I won't show all the experimental data that we have available. This is just some of the more recent stuff looking at ranges of ammonia, ranges of blends of ammonia and hydrogen. So all the way from 0% hydrogen in ammonia up to 70% hydrogen in a jet stirred reactor at lean conditions at 1 atmosphere. And you can see here as you go from pink down to green, conversion of ammonia happens at lower temperatures when you add in hydrogen. And more recent models which account for the latest chemistry, as I mentioned, in terms of HO2 effect, NH2 plus H, and also the thermal Denox mechanisms are better able to capture the recent hydrogen ammonia data that's been acquired. And also we have measured things, these are experiments on accounts. We also measure NO as an intermediate and N2O. So clearly, if you're trying to capture these species, you need accurate NO chemistry in these models. And we can now start to understand what is the effect of hydrogen on blending. So as we mentioned before, in the blue, ammonia, main intermediate is NH2. The chain branching reaction in the presence of NO forms NNH and OH. And then you have the chain termination reaction in the presence of NO to form N2 and water. So these are the main two competing reactions when you're looking at ammonia oxidation. However, once you have hydrogen, the important chain branching reaction changes significantly. So you now form NH2 as an intermediate, but you have recombination of NH2 plus hydrogen to form ammonia plus H. And then as in traditional combustion, H plus O2 reaction to O plus OH becomes the dominant chain branching reaction and then drives the consumption of ammonia. But also we know that NH2 plus HO2 leads to the formation of OH. So that triplet state reaction that we showed previously becomes even more important in the mixtures of ammonia plus hydrogen, because a lot of OH is being formed by the H plus O2 reaction. So we can say that adding of a hydrogen, okay, it causes recombination, but that leads to the form of an H radical. You get H plus O2 go to H plus O2 going to O plus OH. You have HO2 recombination reaction, and then you have the important NH2 plus HO2 on the triplet and singlet channels that we had seen before. So the first one was a singlet channel H2NO plus OH, and the second was a triplet channel to form NH2 and OH. We also, but at the same time, you have inhibition chemistry. So because you have more OH now, so that inhibits your Denox mechanism. So NH2 plus NO going to form NNH and OH goes down. And so the termination reaction that we talked about before, formation of N2 plus H2O also goes down. And that again leads to more reactivity of ammonia. And in summary, you can say that the chain branching mechanisms have changed, and also the importance of termination in the ammonia mechanism is altered because of the addition of hydrogen. So I'll conclude by saying there's been significant advances made in ammonia combustion chemistry, all the way from fundamental kinetics, rate measurements, but quantum chemistry calculations, the effects of NO, the effect of important intermediate radicals like H, OH, and HO2. And also we have a large number of experimental data that's available. Probably 10 years ago, we couldn't do a comprehensive ammonia combustion chemistry model, but today we have a significant amount of data available. In the presence of hydrogen, that data set is also growing, and we have kinetic models that are able to capture reasonably well hydrogen co-blending effects, but I think there's still more studies that have to be done for hydrogen blended with ammonia. They're limited to flames and high temperature ignition. We probably need some more low temperature studies in ignition devices and speciation in ignition in shock tubes, say in the 800 to 1000 Kelvin range. We know that hydrogen blending now promotes the conversion of ammonia at the given temperatures. One thing that I did not cover is the effect of ammonia and hydrogen blending on hydrocarbon fuels. There's been a number of studies on ammonia plus methane in Japan, ammonia plus oxygenates here done at KAUST, and in Germany, such as dimethoxymethane, dimethyl ether, and other oxygenated fuels. But I think there's still need from looking at ammonia plus hydrogen plus those different fuels. And what I anticipate is probably in the future, if you were to use ammonia as a fuel in a power plant, you would moderate the amount of ammonia
as well blended with methane or other carbon-based fuels based on the price of electricity. So if electricity price will depend on the consumers and their requirements for low carbon power. And in the daytime, industries might want to pay a premium for low carbon power where you'll burn mainly based on ammonia and hydrogen. But in the nighttime, as those consumers go away and carbon requirements decrease, you'll blend in more methane. But at all times, you'll have ammonia, hydrogen in the mixture. And then it'll be a question of how much hydrocarbon you blend in based on the electricity price that you're trying to achieve. And I think then you come to lots of interesting chemistry that could be studied. So thank you. And I'd like to have any questions during the discussion.
Thank you very much, Mani, for this presentation.